Hi, I'm Xing, and I just finished making version 1.0 of the Arcadia High School 3D map. You can access it at map.ahs.app, where in order to see the 3D version, you will have to sign in with your AOC account. Once you're in, you can click the 3D toggle, and either use two fingers or shift click to rotate the perspective, use a scroll wheel or pinch and zoom to adjust your height, and single finger drag to move about horizontally. Now this map has been built to be very aesthetically pleasing, so you can just sit here all day and look at the sunset and the moving clouds and our wonderful architecture. Or if you are more practical, you can use a search bar to find the nearest snack or restroom, or if you're new to our school, you can find out where all of our classrooms are. This map is currently running very smoothly on my school issued Chromebook, and it also runs quite fast on web browsers, in phones, laptops, all the other stuff. We are planning to port this into our native mobile apps in the next few months, and with it, add things like gyroscope and augmented navigation features. Now, if you're interested in how I made this, we have our source code right here, and essentially, I started this project about a year ago, where I began essentially modeling most of the school based off of satellite imagery in a voxel editor. And from there, I was initially planning to use um, a off-the-shelf library for rendering the voxels, but it turned out that nothing at the time existed that suited my needs of both rendering things in real time and rendering it nicely. So that's why I built my own custom voxel rendering engine, which essentially, first of all, it takes the 3D model and converts it into what's known as a signed distance field. And this is essentially a lattice representation of the closest, well, let me find the code. Essentially, it's a lattice representation of the closest, or the distance to the nearest block on every point in this 3D volume. And with this information, we can very efficiently ray trace a ray from any surface at any other angle. So for instance, to calculate the shadows which run in real time, I simply run a ray marching algorithm up towards the sun and see if it hits something. If so, it's a shadow. Otherwise, it's lit by the sun. I can also use this ray marching algorithm for other things, like for example, in the version 2.0, I'm planning to implement reflections and refractions, which currently I had to drop because they don't work on certain browsers, Firefox. But anyway, in this beta version, you can sort of see how there are actual reflections on this on this rough surface, and here I sped up the time so you can see the shadows evolving in real time. Unfortunately, I had to disable this for version 1.0 because of compatibility issues with certain browsers. But there are also lots of other technologies involved. So this whole thing is supported by a mountain of linear algebra. So if you're currently learning pre-calculus at school, this is some application of your gruesome homework. So for instance, um, here in the navigation algorithm, we have to use a projection matrix in order to convert the scene from 3D into a flat thing that the computer can see. And the same projection matrix is applied to all the labels to make them seem to stick to the buildings. Even though the labels aren't rendered with alongside the rest of the buildings, they still are attached stationarily to them because the same projection algorithm is applied to both of them. And as for other things like the clouds and the mountain, that's all generated procedurally using a bunch of layer noise. So in the shaders files, you can see how, for example, the cloud is really just a bunch of fractal Brownian motion noise layered together, And same with the mountain. The mountain is just a bunch of noise which is faded into the horizon based on the z-axis. The navigation also uses a bunch of interesting methods. So in order to make it feels like when you're moving around, your finger is like sticking to the ground, I have to apply the inverse of the projection algorithm to go from 2D back onto the 3D plane. And that requires finding the inverse matrix to the projection matrix, again, linear algebra, and then calculating essentially where your mouse lands on and where it's going in order to make it appear sticky. Other things, let's see. You can see how here the blocks all get darker near the corners, and this is something called ambient occlusion. It makes things look much more realistic, and I think you can see the better example in the higher quality beta version. For instance, here, and if I just go down real shallow, you can see both the reflections and the ambient occlusion working. And ambient occlusion is another sort of feature of using a sign distance field voxel marching algorithm, which comes naturally. So yeah, this is essentially the 3D map of the school and how it works. If you want to play around with it, just head to map.ahs of the app. And if you want to learn more or want to work on this and other things that the app team is making, feel free to contact us and apply for the team.